serialize a model into a file, like going from the artifact into a file that you can save, it needs to contain all of the information to unpack it back into the model artifact. So for a model file, that's going to consist of the tensors, so the large vectors of the weights of each layer, and the model architecture code to how to put it all back together. And when the model is deserialized back into the artifact, the instructions to put it back together execute automatically, meaning that if a malicious attacker injects the attack into that code, that's going to also execute automatically. So this might not even affect the performance or the output of the model. It might behave just as expected, but be running an attack outside of that behavior. And so this is just visualization of the pipeline between serialization and deserialization, going from the model to the byte stream to an artifact store. This could be something like Hugging Face, and then back to the byte stream into the model. And if a model serialization attack occurs, injected code gets into the byte stream either before it hits the artifact store or if the artifact store itself is compromised. And then when you unpack it, we have arbitrary code execution, leading to basically a modern version of the Trojan horse, where we all remember the early internet days with the Trojan horse viruses, where you think you're downloading one thing, you go to load it, and it's executing other things on your machine. And for these machine learning files, the attacker can do things like steal your credentials or sensitive data. They can poison other models or data sets that are on the same machine. They can open a back door for the attacker to use later. The attacker doesn't have to do anything additional at the time of the attack. They can just let the user download the file and be at risk. So classic antivirus software like ClamAV isn't going to catch this because it's in serialized code. It could catch it if that code was deserialized, but at that point, the attack has already occurred. So the pickle format is especially vulnerable to this. Pickle is the Python native serialization format, and that means kind of by design, any arbitrary Python code can be pickled. And it's been known that opening random pickles is unsafe for a while because this can happen. Fickling, the library that documented model serialization attacks on pickles specifically, demonstrated this and made a pretty famous blog post about it a few years ago, but a lot of these machine learning frameworks still use pickle for serialization. So the classic libraries like scikit-learn and XGBoost definitely do, but PyTorch, which is a very prolific machine learning framework, still uses this. And even more modern frameworks that have moved away from pickle, like TensorFlow and Keras, are still vulnerable to this because they have custom operators and have lambda layers that can include arbitrary code again. So this is not solely a theoretical problem. It's like we did a sweep of files on Hugging Face and found over 3,000 capable of these model serialization attacks. And 41% of them were not detected to be unsafe. Like Hugging Face does do some scanning using Pickle Scan, which is a basic model serialization attack detector, and ClamAV, but it misses a lot of them because these models are just very easy to share on these hubs due to the community nature that we talked about earlier and the ability to use name squatting and riding on the publicity of very big famous models. We've often joked that the easiest way to do this would be to just download the current iteration of Llama and make a slight update so it seems useful, inject code, put it back up, call it something like Llamas with Hats or something, and users would just download it because they feel like they have no reason not to trust it. It's on this community and be at risk. We saw an especially suspicious one where it was name squatting on 23andMe, where it looked very convincingly like 23andMe, but it had some of these attacks in it. So yeah, Hugging Face misses some of these because it's out of scope for them to be policing everything that's on their site. It's very user-driven, so they say that it's your responsibility as a user to check whether things are safe. And how do we do that? One answer is the tool ModelScan. ModelScan is an open source tool to detect model serialization attacks. It's free through pip or through cloning the GitHub, and it detects these malicious operators in the file without needing to deserialize and put yourself at risk of the attack. So it supports all of the pickle-derived formats, including PyTorch, and a few that are other formats that are still vulnerable to these attacks. So this is just an overview of what we're doing for each file type. For pickle-based ones, we're scanning by opcodes and kind of reconstructing the stack of what would end up executing and looking for things that are known operators that can be used to craft attacks like exec, eval, os, runpy, yeah. For TensorFlow, looking for custom operators. Keras, there's the Lambda layer. Anything that can be used to execute something malicious extra. So knowing about this tool, when would it be useful in the machine learning lifecycle to use it? And a good heuristic is anytime the file is changing hands. So definitely if you're downloading any of the public foundation models, anything pre-trained by someone else, scanning it before you go to load it is a really good practice. And another time is if you're uploading to a model registry or putting it into storage, putting it into an artifact store, knowing that nothing in your pipeline introduced any vulnerabilities that you didn't know about it is useful. And then also, before you deploy any models into production, anything that would be interacted with by a user, by another part of the organization, definitely want to scan it to make sure that it's safe, it's not introducing more vulnerabilities that would snowball. So this is just a sample output of ModelScan as a CLI tool. It can be used as a Python SDK as well. The CLI tool is very easy to use, just passing in the path of the file. And by default, it gives this console human readable format, listing out the issues found and ranking them by severity. So this example is one that is a Keras file, had a Lambda layer that has arbitrary code. And yeah, there's also an option for a JSON format or customizable format or adding custom scanners in the settings. So it's really trying to be as modularized and configurable as possible so that people can use it in a CI/CD pipeline. So with that, I'm going to hand it over to Will to talk about further risks.
Awesome. Yeah. Thank you so much, Sam. So yeah, now we're going to talk about some risks in private model registries. So in contrast to public model registries, where the goal is to share your foundational models with the community and have them be openly accessible and readable to anyone in the public, a private model registry is generally meant to store proprietary or private models that an organization does not want to be exposed to the outside world, either because they're maybe trained on PII data or because these models are some sort of trade secret that they would consider their own proprietary information. And so there's a ton of options for different private model registries that companies can use. And there's anything from MLflow, which is an open source framework that companies can deploy within their environments. There's several commercial offerings such as Weights and Biases, and all of the major cloud providers have registries such as SageMaker Model Registry. And then there's also always the option of foregoing all of these nice features of a model registry and just dumping your models into an S3 bucket or some other form of cloud storage. But I'm sure no one is guilty of that in this room. So we know that these private model registries are safe, right? We know that they're deployed within our environment. Only people within our environment have access to them. And we know that hopefully everyone in our company is compensated well enough to not be introducing these attacks themselves into these models. So we think that these should be safe, right? Well, of course, this would not be a very long presentation if that were the case. So let's challenge some of these assumptions. So to start, our security research community, Hunter, has found over 20 vulnerabilities in the MLflow framework alone in the last year. And this is the same framework that several companies are deploying as their private model registry within their own organizations. And a significant number of these 20 plus vulnerabilities would allow for complete system takeover of that MLflow server. And what that means is that any attacker exploiting these vulnerabilities could have the ability to both steal models that are proprietary, but also even overwrite those models with potential new vulnerabilities. And if you're part of the camp that is putting their models into cloud storage like S3, then we've actually found that up to 46% of these buckets that are storing models can be misconfigured to allow for additional access by unexpected users. So in other words, people that you would not expect to have access to your models either within your organization or from outside of it can read your models from this bucket or even write to them if you have configured your S3 buckets improperly, which, let's be honest, everyone has missed some IAM configurations every now and then and can be vulnerable to this. So what can you do about this fact that your models, your private models, your IP are not as secure as you might otherwise expect? Well, one thing you can do is you can always scan your private models with model scan. So just like Sam suggested with these public models, we can always make sure that our private models have not been tampered with and had any model serialization attacks injected into them without our knowledge. But we can even go a step further within our private model registries to make sure that they have complete security for making sure that they haven't been tampered with at all. And the principle that we're going to use for this is something called zero trust architecture. And zero trust architecture is basically the idea that you shouldn't have to implicitly trust any single entity in your entire system. You can basically treat any single part of your system as if it's an external system, something completely untrustworthy, and you can build up trust from, some sort of provable principles. So to explore why zero trust architecture is important, we can go over some pretty scary hypotheticals. So to start, what would happen if an attacker gained access to one of your systems? For instance, one of those private model registries that we were just discussing. So it would be a free-for-all. They would be able to do whatever they would want to those models. They could, like we mentioned, inject model serialization attacks. So that would be a concern, but hopefully that would be mitigated by model scan. But they could even be more nefarious, and they could modify the models in even more subtle ways. So they could, for instance, use a model poisoning attack to change these models in your storage. And as an example of a model poisoning attack, say you have a model that identifies street signs, and it can identify stop signs and yield signs and speed limit signs, and it just takes these images as inputs and classifies them. An attacker, if they got access to this model, they could use as few as just 2 or 3 additional pieces of training data to fine-tune that model, and they could give it, for instance, training data that says a stop sign with a blue sticker on it should actually be classified as an 80-mile-per-hour speed limit sign instead of a stop sign. And with just these 2 very small pieces of training data, a very, very small tweak to the model, now your model will think that any stop sign with a blue sticker on it, that of course a human would recognize as a stop sign, is actually an 80-mile-per-hour speed limit. And so this would be a massive concern and a massive risk. And unfortunately, model scan doesn't pick that up because it's not a model serialization attack. It's simply just a change in the way that the model is trained. And so that raises the question of, well, how do we know that these models sitting in storage haven't been tampered with at all? How do we know that, some attacker hasn't gotten their hands on them and done one of these model poisoning attacks? So the way that we can do that is using the technique of cryptographic signatures and verifications. So signing and verifications is a foundational piece of zero trust architectures because it basically removes any of the implicit trust you have with when dealing with software artifacts. So it allows the trusted author of a given artifact, such as a machine learning model, to use their identity to verify that a certain artifact is safe at a certain point in time, and that at any point in the future, anybody else can verify that signature and verify that this model is the exact same one that that initial author created, and there hasn't been any changes or any tweaks to it since. And so this removes the implicit trust of having to, take a model out of your registry and just implicitly trust that it's safe to use because it's from your private registry. Now you can actually have this cryptographic verification that guarantees that it is actually safe to use. And so the tool that we'll talk about using for doing this signing and verification is called SigStore. So SigStore is an open source tool from the Open Source Security Foundation that allows developers to sign artifacts using only their digital identity. So what that means is, whenever you log into Google or to GitHub or something like that, you're basically proving your digital identity by by providing your password or your two-factor authentication code. So SigStore lets you take that digital identity and tie it to an artifact that you've created, such as a machine learning model file, and basically say that as a trusted developer, for instance, if Sam's a trusted developer, she can log into her Google account and sign this artifact, and I know that Sam produced this exact model artifact at this point in time, and I can trust it. And if it has varied at all whatsoever in the future, then SigStore will tell me that her original signature isn't valid anymore. And so this whole principle of zero trust architectures and using SigStore for signing artifacts has actually been in practice for quite some time in traditional software. So we can start by looking at how this is used in practice to make things a little bit more concrete with a traditional software use case. So in this case, we're going to look at how we can secure software containers. So a software container is basically just a way of storing and running code in a portable manner. So when you want to deploy a container securely, you're going to start by obviously building it, writing some source code, and then shipping that into a container image. You want to scan it using a traditional antivirus scanner, such as ClamAV, to make sure that there's no malware or anything like that in your container image. And then once you have produced this container image, made sure that it's safe of malware, that's when you can use something like SigStore to actually go ahead and sign the container image with your identity, and that basically gives it your stamp of approval to say that this container image is from me, is from Will or from Sam, and that you give it your stamp of safety. And then it can go to any container registry for however long you want and eventually be pulled down, and whoever pulls it down can verify that that signature is the same as it was when it was initially uploaded, so that there has not been any tampering done to that container image. So this exists in production today in a lot of systems for traditional software, and we think that we can also apply it to machine learning development cycles as well. And so the way that we're going to apply it to ML development is actually going to look very similar to how it's done today in traditional software environments. So instead of starting with writing some source code, we're actually going to start by running some experiments in, for instance, a Jupyter notebook to train an initial model. And once we've produced a model that we're satisfied with, we can serialize it into a actual model file. And as Sam has mentioned, we always want to scan our model files the moment that we create them. And so this time, instead of using a traditional antivirus, we're going to use model scan to make sure that during the build process, none of the model files have got any viruses from the build process. Once we're confident from model scan that there are no issues with the model file and that there are no potential model serialization attacks, then we can actually sign it in the exact same way we would a container and give it our stamp of approval using our identity to say that, you know, I will, as the developer of this model, say that it's okay to use. And then we can upload that signature in addition to our model to our private model registry like MLflow or like S3 or whatever else we'd want to use. And we will know that as long as that signature stays with that model, we don't really care what happens to our model registry. Even if it gets tampered with and even if the model is changed significantly, then that will be taken care of on this next verify step, because if there's any changes to the model while it's sitting in storage whatsoever, this verification step will fail because it's not the same artifact that we originally signed. Whereas if it is the same artifact, then this verification will succeed and we can confidently deploy it into our production application and have absolute confidence that this model file is the same one that we started with. So this is basically how we envision using these zero trust principles to scan, sign, and verify any of your machine learning models when they're going out into production. So overall, we covered a lot of ground, and if there is nothing else that you take away from the presentation, then the three main things are that first, any model file can be vulnerable to a model serialization attack, because any of these model files are going to be executing some kind of code to unpack themselves when they're getting deployed. So any model is vulnerable to an MSA. As a result of that, you should always scan your models with model scan to detect these model serialization attacks. And then lastly, especially when you're dealing with private models, you should implement a signing and verification mechanism using SigStore to always establish the authenticity and integrity of those models and make sure that they haven't been tampered with in any way.